Okay, so let's compare the previous following four molecules that we discussed, and let's compare their boiling point from lowest to highest. Okay, so before we start with that, the boiling point is basically a physical property. Okay, so what is a physical property? Well, physical properties have to do with intermolecular forces, right? Really how strongly or weakly molecules are packed. So how densely the molecules are packed or how scarcely the molecules are packed, right? And physical properties, so some examples of physical properties, I think the more common ones you're going to start to see is, boiling point, right? Condensation points, any type of phase change points, as well as phase change. So solid to liquid to gases, right? Phase changes are also examples of physical properties, and you can understand how phase changes occur when heat is added or when heat is lost by assessing physical properties, specifically by looking at intermolecular forces. Another really common one is solubility. So these are common ones you're going to see throughout your career in chemistry. And really, intermolecular forces at the forefront of this. So that's why we were assessing intermolecular forces, to be able to do a question that is something like this, right? So we looked at these molecules. We looked at the structure of the molecules. I'm just going to reiterate that really quickly. So we looked at chloromethane. So chloromethane kind of looks like this. Okay, you can review. Hopefully you went through the videos, or you can always go back and view those videos if you didn't understand how we created the structure. And we did the electronegativity difference, and we found this was negative. Right, so this was chloromethane. Right, we also looked at, whoops, sorry guys. We also looked at formaldehyde. Okay, so formaldehyde looks like this, right? And we looked at the electronegativity difference between carbon and oxygen, said it was a polar covalent bond, right? So it looks like that. We also looked at methanol, right? Methanol essentially looks like that. Right, and we found that it had two dipole moments, right? So the net dipole moment was going this way, right? This was also polar. So all four of these molecules we actually found were polar. So acetone, we said it looks like this. I'm going to abbreviate the methyl groups here because they're not important in the overall scheme of the polarity. Looks like that. This was partial negative, partial positive. Okay. Now let's also write down the intermolecular forces that each of these contained. Okay, and we noted that chloromethane, these are all polar molecules, so they all have London dispersion forces. This has dipole-dipole forces, but it doesn't contain hydrogen bonding, right? Hydrogen bonding is between hydrogen and the three most electronegative species, right? It's between hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluorine. Okay, so this by default doesn't have hydrogen bonding. Formaldehyde, because it is polar, it has London dispersion forces, dipole-dipole forces, but it doesn't have hydrogen bonding because what we're looking at right now, boiling point, this is a type of physical property that involves cohesive forces. So cohesive forces are forces between the same molecule. So there is no hydrogen bonding here, right? You can understand this if you put another formaldehyde molecule next to it. This is partial negative, this is partial positive, right? And you would notice that the positive and negative regions would attract, right? So you would see the dipole-dipole force here. This is where the dipole-dipole force would be located, but there is no hydrogen bonding. Hydrogen bonding is specifically where there is a very significant or a very stark dipole-dipole force. That means there is a really high electronegativity difference, and you only see that between hydrogen and the three most electronegative atoms. So methanol, we said it had London dispersion forces, dipole-dipole forces, but it also had hydrogen bonding, right? That occurs because of this oxygen, this hydroxyl group, right? It's an alcohol, it tends to have hydrogen bonding, right? Acetone, we also stated earlier that this had London dispersion forces, dipole-dipole forces, but it didn't have hydrogen bonding because of the fact that when you bond with it, it's only the carbon and the oxygen that interact. And you can see that here. Let me just orient the molecule this way so we can show this more clearer. This is positive, this is negative. Right? You would have a dipole-dipole force between this oxygen and this carbon, negative and positive, and this carbon and this oxygen. These are dipole-dipole forces. Okay, so now we have all the intermolecular forces written down. If we're comparing each of these four molecules based on boiling point, the molecule with the highest boiling point will technically have the strongest intermolecular forces. And if hydrogen bonding is present, then it's going to take the stage as basically having the highest intermolecular force. So methanol actually is going to have the highest boiling point out of all three of these. Okay, so this is going to be on the far right. So we've considered methanol. Now we have to compare acetone, formaldehyde, and chloromethane. Now this is where it becomes a little complicated because of the fact that these are all polar molecules. We need to assess how strong the molecules are in terms of their dipole-dipole forces. Okay, so if we're looking at their dipole-dipole forces, we need to look at the strength of a dipole-dipole force is associated with the magnitude of the electronegativity difference of what creates the dipole, right? So essentially we're looking at the magnitude of the dipole moment, right? So the larger the electronegativity difference, it usually means there's a larger net dipole moment, which usually means there is higher dipole-dipole forces, okay? And based on what we looked at, right, the electronegativity difference between acetone versus formaldehyde, right? In this scenario here, the acetone versus formaldehyde, they both have a carbon to oxygen double bond. They basically have an electronegativity difference between carbon and oxygen. Right? And we calculated this earlier as 0.89, right? Versus the electronegativity difference between the chlorine and the carbon. Right? And if you don't understand how I got these values, you can just kind of view the previous videos. Right, but all I'm doing is I'm subtracting the electronegativity values, and these are the values that I'm using. For carbon was 2.55, for chlorine it was 3.16, and for oxygen we're using 3.44. So you can subtract it and verify those values. Right, so because there is a larger electronegativity difference between formaldehyde and acetone for the carbon to oxygen bond, then chloromethane is actually going to be the weakest in terms of the boiling point. Okay, so we're going to put this at the very far left. Okay, so we have chloromethane, then we have two spots here, and then we have methanol. Methanol had the highest boiling point, right? Chloromethane had the weakest boiling point. Okay, so we're kind of basically doing this on process elimination. Now we have to compare formaldehyde and acetone. So which one is essentially more polar, right? Now the thing about this is that you can look at it one of two ways, right? So we've looked at, they both have equal number of dipole-dipole forces, right? So in this case, the dipole-dipole force of formaldehyde was greater. So the dipole-dipole force of chloromethane was weaker than the dipole-dipole force we would see in formaldehyde, or the dipole-dipole force we would see in acetone. And that's what we've come to a conclusion of. Because formaldehyde and acetone have the same dipole-dipole force, we're looking at these two, then what you can do here is we can assess Lens dispersion forces. So usually what we do is we can assess lens dispersion forces and look at the size of the molecules. The larger the size of the molecule, if we have a larger surface area that's usually correlated with molecular weight, then we usually have greater London dispersion forces, because greater the size of the molecule, greater the surface area, there's more room for contact, right? And London dispersion forces are dependent on that. The only problem with this method for polar molecules is that the more nonpolar chains that we actually have, right, the more nonpolar chains that we have, like for instance the presence of methyl groups, which we see in acetone, these methyl groups are very nonpolar. So these are nonpolar methyl groups. So you can make the description here, you can make the argument here that because of these nonpolar methyl groups, they actually reduce the polarity, or they reduce the dipole moment of the molecule, right? They make it more nonpolar, right? Versus the hydrogens here, they're not too bulky in terms of a nonpolar group, so as a result, there's a stronger dipole moment generated. Based on that assumption, then formaldehyde should have a higher boiling point than acetone. Now, this is one description of it, and I mean, there is no right or wrong answer in this scenario, because what you want to do is you want to explain your reasoning, right? Although, there is a general order of this question, there is a correct answer to this question, but you want to explain your reasoning as much as possible. You can't just say formaldehyde is greater than acetone, and just leave it at that. You have to explain your reasoning. The reasoning for this is because acetone itself has these bulky methyl groups, these non-polar methyl groups. It's actually going to reduce the overall dipole moment of the molecule, so it makes it less polar. It makes it less of a polar molecule, so it actually weakens the dipole-dipole force, right? So this tells us that the dipole-dipole force of formaldehyde is greater than the dipole-dipole force of acetone. This is just based on the lack of excessive nonpolar methyl groups, right, or nonpolar substituent groups. Substituent groups are attached groups to the central atom. Okay, so this is the idea behind it, and what you could do is you could verify the boiling points of each, right? Now, if you had just completely nonpolar molecules that you were looking at in terms of the boiling point, then you would just compare based on London dispersion forces. So in that scenario, you would just look at the molecular weight, which had the higher molecular weight, and as a result, there is a greater surface area and greater London dispersion forces. So this works really well with nonpolar molecules. But with polar molecules, guys, you have to make sure you understand that if you have more methyl or nonpolar groups, methyl groups being one type of nonpolar group, if you have more carbon and hydrogen chains in the molecule, it actually reduces its overall polarity, and it actually reduces dipole-dipole forces. So this is going to be the best way we can describe the boiling point. Okay, so try to go through this, try to go through the other videos, see if you understand this, and if some of this stuff is a little hazy, I've also attached a breakdown of this material that includes VSEPR structures, Lewis dot structures. It also goes over intermolecular forces in a lot of detail and some examples of physical properties. So not only does it look at boiling point, but it also takes a look at solubility. So give that a shot, and stay tuned for more content on chemistry. Congratulations on finishing the video. To reward your attention and determination to learn and enhance your skills, we've created a new reward system this year. Each time you complete a video, you will be rewarded IQ points. Depending on the length, difficulty, and type of video, instructional versus question-based or both, you can be rewarded different levels of IQ points. These IQ point rewards will be either 10, 20, 50, or 100 points. Our goal for implementing this system is to enhance your motivation and improve your daily productivity. Use the amount of IQ points you earn each day to reinforce and gauge your commitment towards your education. And while you do this, remember to like, comment, subscribe, and share our videos. Your continued support will assist us to release more free educational content in the future. Our collective goal at Course Concepts is to assist you towards academic success, one step at a time, because success starts with a single concept. So we want to thank you for being a member of Course Concepts.